All right. So it says how many tangent lines to the curve, yada, 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 pass through the point 1, 2, and then at which points do these tangent lines touch the curve? Okay, so what I'm going to do is I'm going to start by writing a general equation for a line, or for a tangent line, where I'm going to use the generic slope by the derivative. So I'm going to write like I'll write something like this. Is that okay with everybody? Now, to calculate that dy dx, I need to have, I need to use the quotient rule, right? Since that's a quotient, there's no other way to kind of go about doing that. So that's going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So when I do that, I get x plus 1 minus x over x plus 1 squared, or 1 over x plus 1 squared. Okay. So this is going to act like my slope then. And I want to see if we pass through the line or the point 1, 2. Now the key thing to remember here is that like this x and then the x in my derivative don't have to be the same x. Is that okay with everybody? Because that tangent line, you know, like if I have whatever curve and say like, here's the point 1, 2, I could have something like that going through it, where the slope of the tangent line is based on this point, but it still ends up passing through that one over there, right? So that's why I'm going to just plug the x into the x part of the equation for my tangent line, but not into the slope form. Okay. So what can I do with this now? Let's see here. So I have 2 equals 1 over x plus 1 squared plus b. Guess I'll move that b over to the other side. And then make a reciprocal to get the x's out of the denominator. And we'll do something like this, I guess. So I have that would tell me the points that I can pick, or those will be the points where I can place a tangent line where it could go through that point, right? So clearly there's some values of b that's not going to work for. Is there a better way of doing this than what I'm trying to do? Let's look at what somebody spent more time thinking about this than Mr. Kulik did. if they have a clever approach here. Did you check in the back of the book, Mia? This was an odd.
I just eyeballed it. Like I grabbed it and I was like, oh, that looks right. So I got it. That's like what I got it. I put 2 and it was like 0, 0, and 1, so. I got 0, 0, and then I got -2.
Okay. Okay. Shh. Right. Okay. So I had the right idea. We're just going to do a little bit better with this piece here. So let's talk about the point x equals a. So in that case, our slope becomes 1 over a plus 1 squared. And then if I plug a into our function, I have the point a over a plus 1. So that's what I'm going to do to write my equation for my line. Does that feel okay? And then if I plug in my point, now I just have a single variable rattling around in there that we can deal with. So now this just becomes a pain in the butt algebra problem to find my values for a. Is that okay, Mia? Yeah. So I'm going to multiply both sides by a plus 1 squared. And then, let's see, that's going to be 2a squared plus 4a plus 2 minus a squared minus 2a minus 1 plus a equals 0. What's up? Just should be one of them because one of them canceled when I multiplied to that thing, right? But yeah, please keep on, following along. And if it looks like I made a mistake or you're not sure, like holler at me. That's exactly what I want you to do. Let's see. So I have those guys give me a 1a squared, and then I have 4a, 2a, 3a, and then 2 minus 1 is 1. Mr. Kulik, you're dumb. Because that's just supposed to be a 1a there, not a 2a. Great googly moogly. It's like, that's not looking like the thing I'm supposed to be getting when you told me it was like 2 root 3 or 2 plus or minus. Anyways. So there's that. Everybody's cool? To solve this quadratic formula, so I have 16 minus 4 is the square root of 12, which is 2 root 3. And then I reduce that. So I have two values for A that should pass through that point, or whose tangent line should pass through that point. To find their y-coordinate then, I'm going to plug this back into the original function. Oops. Just pluses. And I guess I don't know, did they rationalize that that denominator there when they wrote the answer in the back of the book, or did they just leave it as a fraction? They probably rationalized it, didn't they? Yeah, all right. Well, let's do that, I guess. What's the conjugate here that I should be multiplying? -1 minus root 3. Let's see, so we get 2, and then 2 root 3s, and then minus root 3, and then minus 3. So that's going to give me -1 plus root 3. And the bottom, I'm going to have 1 minus 3, so that's -2. So that's going to become 1 minus root 3 over 2. So there's one answer. Well, the calculus part was relatively straightforward. We did one derivative and made a tangent line.
Right.
From there, after, it was all just like annoying algebra.
Yeah.
So that's one answer. To get the other answer, what are we going to be doing differently? Yeah, we just have to do the other version. So when I do that, I'm just going to write it down because I hope that nobody's surprised that that's the other version. But you could grind through the algebra yourself, or the simplifying if you wanted to. But that's the other answer. Just the only difference is the plus sign on the y-coordinate instead of a subtraction sign. Which again, you should be expecting almost identical, since it's the conjugate that you're grinding through. Mia. That bit off more than I think I wanted to chew on that problem. I was hoping that they would have given you integer solutions for A. That would have made life a lot nicer. Sophia?
Can you do 53 on 3.1?
Mm-hmm. So what page was 3.1 on? 182. Show that the curve yada 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 has no tangent line with slope 2. So that what we want to do is, this is basically asking us to show that if I set the derivative equal to 2, that's going to have no solution. Okay? So first order of business would be to calculate the derivative. So the derivative of 2e to the x is just 2e to the x. The derivative of 3x is 3. And the derivative of 5x cubed is going to be 15x squared. Does that all look okay so far, Sophia?
Yeah.
Okay. So we'll set that then equal to 2. And we have this. Now, I can't solve this algebraically directly, but I don't need to solve it because all I need to show is that there's no solution, right? So if I look at this, what can I say about e to the x? Since it's an exponential, has a positive base, it's always greater than or equal to 0, right? If I put a negative in there for x, I'm just going to get like 1 over e, which is still a positive number. You know what I mean? So I can say that. How about 15x squared? What can I say about that? Also has to be positive, right? Because I have something squared. So let's just assume that we have the minimum values. Right? So just take the smallest thing that those two can be.
We're always adding 3.
Yeah.
Makes sense.
And that's what you would do. Again, algebraically, nothing I could do with that aside from like graphing it on my calculator and trying to find an intersection or whatever, but I'm not going to be able to algebraically solve for x because I have an exponential mixed with a polynomial, and there's no good way for us to reconcile that. But since I didn't need to actually solve for x, I just needed to show that it doesn't have a solution, that I was able to kind of sneak my way through and get around having to actually do real algebra there, which is pretty sneaky. Is that a follow-up to this one, Paul?
No,
Okay. Mackenzie or... Okay. Victoria?
Can you do 75 on 3?
75 from the same section? Okay. Where is my insert screen clipping? Okay, so it says find the values for m and b that make f differentiable everywhere. Well, here's the first thing I know, or first thing I'm going to observe, is that over its domain, I know f of x equals x squared is differentiable from negative infinity to 2. And I know that f of x equal to a linear equation is going to be differentiable over its domain. The question is, what about when x is equal to 2, where those two things have to hook together, right? That's the place where I have to worry about. Victoria, are you good with that so far? Okay. So for that to be the case, I need the slope from the left to equal the slope from the right. So if I go from the right, I'm sorry, from the left, so that's the derivative of x squared, which should equal to 2x. And then if I evaluate at x equals 2, that slope needs to be 4. Cool there?
What's that line? It's like 2x line, x line.
So that's a notation that says, and then I'm going to evaluate this at x equals 2. Yeah, so that's just like a vertical bar.
So when it's like, oh, what's the slope of it? You just find the derivative, like slope and derivatives.
I can use the derivative to get a slope. Yep. Or I can use what I know about the slope at a point to tell me about the derivative.
Okay, so you just said derivative of x squared equals some 2. You said 2 times 2 equals 4 because you plug x for 2.
And then I know that this is happening at the point two, 4.
Sorry, why are we doing x equals 2? What was he saying in the problem?
X plus 2.
No, x equals 2.
Because that's the boundary between the two. That's the only place where where this might not be differentiable.
Right, okay.
Because everywhere on x squared I can differentiate, everywhere on a linear I can differentiate. The question is, when I hook them together, can I still differentiate there?
Okay.
When you say like it's not differentiating, does that mean that it's like not?
So if it's not differentiable, it does not necessarily mean it's not continuous. Although if it's not continuous, it will not be differentiable.
What is differentiable?
Means you can take the derivative and evaluate it.
Okay, so it means like you might not be able to do it.
Right. You can have something that's continuous that's not differentiable. Like this is continuous everywhere, but it's got a corner in it, so it's not differentiable. And then you could have something that's not continuous, and that's never going to be differentiable at the point of discontinuity. What we have to make sure is that we cover both those bases, is that we don't have a corner and the two pieces hooked together. Right? That's what I'm basically trying to do. So to make sure I don't have a corner, I need the slope. To make sure they hook together, I need the point where x squared ends at.
Oh, right.
So I'm going to use these two things to write my y equals mx plus b equation.
Which is the right.
Which will be give me the right, yes. So I'm fixing the slope from the right to be 4. So I've done that, right? Now the slopes match, so the right hand and left hand slopes match. And so when I do that, I get b is equal to -4, excuse me. So y equals 4x minus 4 should be my equation. And I'm all done. So here's my m. There's my b. Does that feel okay?
Like you just find the derivative of it, of like the first one, and then you plug into two and see that like that this one. Yeah, I got it.
Yeah, so again, what I did was the piece that I didn't know about was the part I don't know anything about that because I don't know m and b. So I'm going to take the part I do know, figure out what point does that end at, and what's the derivative at that endpoint. And then for the other half, I need to make sure the other half starts where the first half ended, and that its derivative has the same value as the left half did. Does that make sense?
You scroll down a little bit so I can see that.
Oh, yeah. Elvis, you had a hand?
So how do you know MX is B?
Because it's a polynomial. Polynomials will be differentiable over their entire domain.
And to get a slope, we plug the x value into the derivative.
Correct. Yep. So that boundary, where it changes from quadratic to linear, what happened at 2. That's why I plugged that x value in to the derivative to get the slope. Because I need that boundary where it changes function type from quadratic to linear is the only place where I have to worry about. Because if I don't connect them, it's not going to be differentiable. And if I have too steep of a corner, it's not going to be differentiable. So I had to make sure I hit both of those, that I got the continuity piece and then the derivative, the left hand and the right hand derivative there match up. And we've seen a bunch of problems like this that we've been looking for continuity or differentiability, where I've given you where you've gotten a linear piece and a quadratic piece. And I think all of those examples prior had been not differentiable, either because they didn't hook up together continuity-wise, or the derivative evaluated to different values at the left hand and the right hand. Here's an example of a situation where it is possible to hook up a quadratic and a linear and still end up with a function that's differentiable everywhere. Paul?
So you're getting 4 for n, you're getting 4 from plugging 2 into
the derivative.
Okay. And then when you do f of 2 equals 2 squared, that's where you get your x and y.
Right.
Okay, so I see.
Mackenzie? 3.1, number 55? Okay. Is this going okay, guys? What we're doing? Oh, where did that go? Yeah. Cool. Why did it put it there? I just stuck it down there, so anyways. I don't know. All right. Find equations of both lines that are tangent to the curve, yada, 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 and parallel to the line, yada, yada, yada. Okay? So what I'm going to do is this line, what I need is the slope from this line. So if I want two lines to be parallel, what do their slopes have to be? The same. So this would be y equals 12x minus 1. So I need my slope to be 12. So for the tangent line then, I know its slope is going to be of the form 3x squared. So when I plug 12 in, and I solve, I get x is plus or minus 2. Okay with that? Okay. So I know my slope. I'm going to use this to get my point. Where am I going to plug this in to get my point? Into the original. So I have the point 2,9, and I have the point -2, -7. So my first tangent line, my slope is 12, and I'm going to pass through the point 2,9.
All right, no, it wasn't no difference.
24, or -24 plus 9 is going to be -15. And then my other tangent line, again, has slope 12, but it's going to have the point, or pass through the point -2,7. So that's going to be 24 minus 7, so that's going to be 17. So those should be our 2 points there, Mackenzie. Does that feel, or 2 lines, excuse me. Does that feel good? So again, the calculus piece of this was pretty light, right? We had to take one little measly derivative and use that derivative to solve for a value of x. And then we're just writing equations for lines, you know? We had to retrieve the points. But again, that's like kind of algebra 1-y feels almost.
Could you do number 55 on 3.2?
Sure. Okay. It says find r prime of 0, where r is this function. And it says, hint, instead of finding r prime first, let f of x be the numerator and g of x be the denominator, and then compute r prime of 0 from f of 0, f prime of 0, g of 0, g prime of 0. This was 55 on 3.2. So what this hint is getting at is that the quotient rule is going to say that this is going to be, if the numerator is f of x and the denominator is g of x, that this is going to be g of x times f prime of x minus g prime of x, f of x, all over g of x squared. And because this function we're given is pretty kind of gross looking, I can evaluate this a little bit easier if I just do like f prime of x. And if I do that, f prime of 1 is going to, 0 is just 1. And I guess I should probably write f of 0 there trivially is just 0, since everything has an x in it. G prime is going to be, 9x squared plus 36x to the 5th plus 81x to the 8th. So g prime of 0 is 0, and g of 0 is 0. Oh, I'm sorry, is 1. So if I fill everything in now, I have 1 times 1 minus 0 times 0 over 1 squared. So it's just 1. What the book was hinting at is that if you're doing the quotient rule and your like your rational function, your fraction is kind of complicated, sometimes it just makes it more sense to just write the formula down, do the derivative of the top and bottom separately, especially if you're going to just evaluate for a value, than like carrying all that nonsense through and trying to simplify all the x's and everything. Like just do the easy derivatives, plug that stuff in, plug back into the original parts, and then just like piece it all back together into the formula, because that took, it was borderline mental math, and versus trying to grind through the quotient rule and simplify that down and then plug zeros in, it kind of is a nightmare. Victoria?
So should I like simplify, should I take the derivative? Like for like the original equation, should I find the derivative of that and then put it in the quotient, or no? No, wait.
So
No.
this expression that I wrote right here is the derivative of r of x.
Yeah.
I didn't bother to find the actual derivative of r of x with x's in it because it didn't want that. It wanted r prime of 0. So it was always going to just be asking me to plug a number in. This method that we used here, where we didn't actually find r prime of x, is much faster than finding r prime of x and then plugging 0 in.
Right, so you just found the derivative of f of x and the derivative of g of x.
Yeah.
You just plug 0 in.
And then plug 0 into the derivatives and the originals and put them into the formula, which was way simpler than trying to grind through a bunch of complicated foilings to have just like everything cancel out.
That's not do it that way.
Yeah. So that's what the hint was getting at, was like, whoa.
For the quotient rule, let's say like there's something that's like find the derivative of like 1 over, let's say, x to the power of 3. Do I use the quotient rule on that, or can I?
No, that would just be a power property.
Okay.
Yeah, you can just write that as x to the negative third and power property that. In fact, you should be looking to make sure you really need to use the quotient rule when you before you use it.
Like there was a lot where I would do like both to like see, and there's both of the answers are like
Give you the same thing.
no, they don't. Are they supposed to even see? Okay,
Yeah.
so then maybe it's-
Yeah.
Good to know.
The other thing that probably worth showing you guys at this point is that when you're doing these derivatives by hand, you can't check them precisely on your calculator, but you can kind of check them on your calculator. So what you can do, let's go find a problem where we did, well, let's just do something silly like this derivative here. So if I take my original and I type that into x1, so I'm just taking the derivative of 1 plus x cubed, and I take the derivative that I found, and I'm going to put that into y2. What I can do is I can't have your calculator can't find a derivative exactly, but it can evaluate derivatives at values. So what I can do is if I go math, and then where is it at? Maybe it's just under the main math menu. Yeah, okay. If I do math and then I do option 8, so I'm going to differentiate with respect to x. I'm going to do this on y1, which is where I typed the original. And I'm going to do this at like the value 2. And I get this value. And then if I take my answer that I did algebraically, which I put in y2, and I evaluate. I'm just checking to make sure that my calculator, when it finds the derivative and evaluates it at that value, is getting the same thing as my answer when I evaluate at that value. Now, to be sure you have the right answer, you'd want to check a couple of different values. And as you see that, like, it's not uncommon when the calculator evaluates the derivative at a point, it's using an approximation to do this, that you're getting something that's really, really close but not exact. But that's a way you can kind of check with your calculator whether you did the derivative correctly or not, is if you just take your answer in the original and you evaluate them both at, you do the derivative of the original at some point and you evaluate your answer at the same point, they should match or be absurdly close to matching like this one is. Nice trick. Okay, what do you guys think? Are we ready to go here with the next stuffs? The good news is here, section 3.3 is super light. And section 3.4 I also think is not too bad. I said 3.4 and I wrote 3.3. So in section 3.3, we're going to be talking about the derivatives of trig functions. So let's say we look at the graph of y equals sine x. Okay, so this is y equals sine x. Let's think about what its derivative is. So let's start with the graph and see if we recognize something here. So at each of these maximum and minimum, or maxima and minima, the humps or the troughs, what's the derivative going to be? So like if I'm here, what's the derivative there? 0, right? And at every one of those spots, my derivative is going to be 0, right? Everybody happy with that? Now let's look at this spot here. Is the slope there positive or negative? Positive. And what does the slope look like it's approximately at that point? If I took that in and put it like right here, it looks like it's a slope of 1, right? Do you guys buy that? Okay. So down here, then the slope would be like -1. And then over here, it would be +1. And the slope down here would be -1. And then +1. And if I connect this together, what does this start to look like to you guys?
Cosine.
Yeah. You're dead on. Let's see if we can prove that. Is that okay with you guys?
Yeah. We're just doing a definition of that, right?
Yeah, basically, we're just talking about derivative rules. I think this is the, I think after the first two, we can get away without having to do the definition. Okay, so if y is equal to sine x, dy dx, I can find by the limit as h approaches 0 of sine of x plus h minus sine of x all over h. Everybody okay there? Okay. What do you recognize here? That's a angle sum formula. Remember last year in Trig and Pre-Calc we had a bunch of angle sum formulas that we could use. I'm going to use the angle sum formula for sine right now. So that becomes sine of x times cosine h plus cosine x sine of h. And then I still have that minus sine x.
Where's the cosine?
That's the angle sum formula
Oh, okay.
for sine. Okay. So I notice now that I have a greatest common factor of sine in those two terms. So I'm going to take just those two terms and factor off that sine x. So that's going to give me cosine h minus 1. And then I still have this cosine x times sine h all over h. Everybody's okay there? And now I'm going to break this thing apart. So I'm going to do the limit for each piece of the products here. And I'm going to choose to keep the h with that second part of that product. And for the second term, I'm going to put the h with the sine. Everybody's okay there with how I broke that apart? So right away, you should notice that, hey, there's no h's in there, and there's no h's in there. Everybody agree? So that part, that limit is just going to be sine x, and that limit is just going to be cosine x. These other two limits, let's just evaluate with our calculator. So I'm going to go ahead and type into y1 cosine x minus 1 all over x. And I'm going to type into y2 sine x over x, and just do a little table in to see what happens when we get really close to 0. Everybody cool? Okay. So y1 we'll do from below first. So how about that? Okay. And who's convinced that that limit goes to 0? I would be, right? I think that's pretty compelling. Now let's do this other limit. Oops. I wanted y2. Okay. Try that one more time. There we go. I think I'm pretty convinced there. So this just all turns down now into cosine, right? Okay. Well, let's do the same thing now, except let's use cosine. Let's see what the derivative of cosine is. Everybody cool with the same plan?
Yeah.
All right. So every place where we have a maximum or minimum, I know the derivative is going to have value 0. Okay. If I look at this point here, the slope appears to be, sorry, right here, positive 1, right? It's okay.
Oh, yeah, there.
And then down here, it's negative 1. Then over here, it's positive 1. And then, oh, sorry, 0 slope there. Forgot to draw that guy in. And then we're down at negative 1. And then we're up at positive 1. And then we're down here at negative 1. So if I draw this now,
Whoa.
what do you notice? That's not sine, though.
Oh, no, it's not.
Look at what sine was. Sine was the black graph up here.
Sine inverse.
It's not sine inverse.
Oh my God, it's secant.
It's just negative sine,
Oh.
right? It's the same thing as sine. It was just reflected across the
I
y-axis.
was excited.
Or x-axis, excuse me.
Really? Math is just so good that
I know. Yeah, no, the logs. Logs are the same off.
Wait, how do you know? Let's get backwards. So, like, how do you know when you were drawing the graph would be like positive up or down? You know what I mean?
The slope.
Like, yeah.
So I looked here. If I draw that line, that's got a positive tangent line. I draw it as a positive slope.
Positive.
Yeah.
Thank you.
Yep. Shh. I'm going to skip the proof for this because it's really the same proof as the other one. You're just using the angle sum formula for cosine in the interest of time. Is that okay with everybody? So here's my question for you guys. What's the derivative of tangent going to be? Well, I don't know, but I know that tangent is sine over cosine. Everybody agree with that? What can I do to take that derivative? Quotient rule, right? So I'll have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared What's cosine squared, or cosine x times cosine x? Cosine squared x. And what's negative sine x times negative sine x? Positive sine squared x. And what's cosine squared plus sine squared? 1. And 1 over cosine squared I could just write as? So the derivative of tangent is secant squared.
Let's do the math. Circle, just sort of Thank you.
Sure. Could I do this same method to find all the rest of the trig functions?
Yeah.
Yeah, since I can differentiate sine and cosine, I can just rewrite each one of them in terms of sines and cosines and apply the quotient rule to differentiate any of them. Rather than doing that each time, let's just write them down, since you got the feel for like what you would do. Sound good? All right. So the derivative of sine was cosine. The derivative of cosine, negative sine. The derivative of tangent is secant squared. The derivative of cosecant is negative cosecant times cotangent. Well, that's weird, Mr. Kulik. Yeah, a little. The derivative of secant is positive secant times tangent. And the derivative of cotangent is negative cosecant squared. Mr. Kulik, should I memorize those?
Yes.
Oh, goodness me, yes. Absolutely have to have those memorized. What's that? Yeah. Yeah. Like all these derivative shortcuts, could you do these things without the shortcuts?
Yeah.
Yes, but come the AP exam, do you have time to do not the shortcut? No.
I don't think that. I think.
So let's do a couple of examples. So let's just say we want to do some differentiating. Say the first one is y equals x squared times sine x. What do you notice here? Product property, excellent. So we're going to have the first part times the derivative of the second part plus the second part times the derivative of the first part. What's the derivative of sine x? Cosine x. Very good. And what's the derivative of x squared? 2x. Done. Can't do anything more with that. Everybody cool? So algebraically, hopefully this is not too big of a deal. What if we have f of x equals secant x over 1 plus tangent x? What am I going to do with that? Quotient rule. Great. So the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared should I just go down rather than horizontal? Okay, what's the derivative of secant? Secant times cotangent. Nope, tangent, sorry. Mr. Kulik's still rusty on memorizing these things too. The derivative of 1 plus tangent is going to be, yeah, 0 plus secant squared, or just secant squared. So I notice here everything has a factor of secant in it, so I'll probably factor that off. And then I'll distribute like the tan through. And then oops, forgot my variable. And then it's just a question of like, what do I really want to clean up here? Do you recognize this as something?
Is that 1?
I think it's -1 sine squared over cosine squared minus 1 over cosine squared. It's going to give me negative cosine squared over cosine squared. So that should just be -1. Oh boy, Mr. Kulik, we're doing this stuff again. All this stuff never goes away. Oops, that's -1 though. No. Yeah, -1. I don't know if I can do any better than that. Let's look real quick. No, that's as good as they did too. That looked good too. Oops. I did do that though. I don't know why I moved that squared. That's an oopsie. All right. You guys ready for the last example here?
Bring it on.
All right. So let's say if f of x is equal to cosine x, find the 27th derivative.
Nice.
Well, let's get going. So that's first derivative is negative sine. The second derivative is going to be negative cosine. Everybody agree with that? The third derivative is going to be positive sine. The fourth derivative is going to be cosine. Look what's happened. We're back to where we started. So this is what we call like a cyclic function. So how long is our cycle? 4. So every four cycles, nothing happens. So I know that like f of the 8th derivative also going to be cosine. The 16th also going to be cosine. The 20th also going to be cosine. The 24th or the 24th, yeah, also going to be cosine. So the 27th should be the same as the third derivative. So it should just be sine x. Look at that. Didn't even really have to take 27 derivatives there. Did enough to find my cycle, and then I recognized after every cycle has length 4, so. More likely than not, if somebody asks you to do a giant derivative like that, there's going to be some easy shortcut through it, like this one. All right, that's section 3.3. We get some new trig derivative rules. And then you have to remember some of your trig identities from way back when, right? And you're like, oh, goodness, Mr. Kulik. Right? And we're going to start 3.4 here. Just start it.
5 minutes.
Do we have just 5 minutes?
Yeah.
Oh, why do I think this next class ends at 15 then, right?
No, that's at the 30.
It used to start at 15.
I don't know then. Yeah, that's fair. 5 minutes is not worth. No. Okay.